Hi, everyone, and welcome to our webinar, Image Classification Using PyTorch in 2020. My name is Helena Barmer, and I will be the moderator today. I am also the founder and leader of People in Data. So People in Data, they are hosting, or we are hosting this event today in collaboration with Facebook Developer Circle. And we have the lead from there with us today, Anna Unger. She will tell you a little bit more about how to join Facebook Developer Circle later on. I see a lot of questions in the chat that you can't speak. It's because only us panelists will be able to speak and all participants are muted throughout this webinar. And I also just want to briefly tell you a little bit about the structure for this event. So you have the Zoom chat. We have already chatted a little bit there. And you also have the Q&A box. So when Pranjal, who I will soon introduce, when he's doing his presentation, you can ask questions in the Q&A box regarding his presentation. If you have any general questions, or if you would like to just connect with each other, connect with us, ask anything, do that in the Zoom chat, please. So Zoom chat for general question and Q&A box for questions for Pranjal. So now it is my honor to introduce you, Pranjal. He is our rockstar webinar instructor. And I can say that because I have worked with you before, Pranjal, so I know this. And he is a rockstar webinar instructor by night, maybe AI mentor by day, should I say. It's my honor to introduce Pranjal Chaubey. Please go ahead. Hello, Pranjal. How are you today?
Hello guys, hi Helena and hi Anna, and to all the participants who are still joining in, a lot of people actually. So yeah, I've been a mentor for AI for the last year almost, and I was a product manager before, and I was handling a fairly large team and a successful product, generating multi-million dollars in revenue. But I got really bored of my job and I decided to take a break, and I figured that I wanted to do something with AI and ML, and learn this technology. I had been quite amazed by the latest advancements in AI and ML that were coming pretty much on a daily basis, and I felt that this is something that I would really want to do and learn. And that's when I started learning these technologies pretty much on my own. And there was a point where I figured, excuse me, there was a point where I figured that I wanted to you know start teaching this, because I feel that the best way to learn a particular concept is to teach it to someone. And that's when I decided to take up mentorship with Udacity. And in the last 1 year, I've pretty much mentored over pretty sure 250 people easily. And my mentees have ranged from people in in the east coast of USA to Europe, India, of course, Middle East, China, Japan, Singapore, Hong Kong, Taiwan, even some people from Australia. And that has been a really amazing experience. So yeah, so I decided to, I wanted to teach what I have learned. I've learned a lot of things, I felt, and it's time to teach. And there was, I joined Udacity as a mentor, and at the same time, I also started, going to these community events. That's how I got to know about Facebook Developer Circles. I joined the Developer Circles in my city, and I met Helena on an online, scholarship at Udacity, and that's how we, started talking. And I did a webinar before with her, and this is going to be my second webinar with Helena. And that's one thing led to another, and here we are hosting a nice workshop for a lot of people. More than 150 people have joined right now, almost. And yeah, so here we are. So I think it's time for me to get started. By the way, I have a screen on two sides. I actually have 4 screens in front of me. So don't worry if I look here and there. Probably I'll just turn off my camera because there are so many people right now. We are a little edgy if there are going to be any audio issues or video issues. So I just turn off my video. Guys, can you hear me? My voice is fine. Yes, yes. Okay, that's great. Okay, so so we'll start off with the image classification using PyTorch in 2020, and from time to time, I'll probably speak a little louder, and that is to basically bring you back, bring your focus back. Otherwise, I'll be like speaking nicely and softly, but from sometimes I'll be like, oh, this is what we are doing. Okay, so it's just to make sure that you're connected. So guys, this is we are going to use Google Colab and for this particular webinar, and I would ask Helena to share the link to this Google Colab. You guys have to open Google Colab on your systems, okay, and code along with me. I'll be coding image classifier live over here, okay. So Helena, can you share the link with all the participants? Yes, guys, that's the link. You guys can see the link in the chat window. Please open that link, okay? And as soon as you open that link over here, the window will open something like this. And over here, where my pointer is, you guys will see an option of open in playground. You have to click that option. You have to open it in playground. Guys, I hope everybody has got the link and you are going to open it. Okay, so in case you guys have opened it, what you need to do is you need to connect this notebook to a runtime. Okay, so how do you do it? You go over there on top, you click on runtime. You click on runtime, you scroll down and click on change runtime type. You click on this. Window like this will open. The runtime type will be Python 3. Okay, you don't change this. The hardware accelerator, we have to select GPU. Okay, you have to select GPU. So Google Colab is basically an online Python Jupyter notebook environment, basically, where you run your Python experiments, and it provides a GPU for free, which is quite amazing, to be honest. And you click on save, okay? You go to runtime, go to change runtime type, select GPU as your hardware accelerator, click on save, and then you click on connect. Over here, you have this button called connect, you click on this, okay? And you wait for a while, it will show it's connecting. Okay, somebody can see the options. I think that's because how Zoom is working, guys. You go to runtime. You click on runtime. Okay, you click on runtime, and then you click on change runtime type. When you click on change runtime type, what you're going to see is, so let me just type it out for everyone. Uh, click runtime above, then click change runtime type, and then select GPU. Okay, then select GPU. And once you do that, you click OK. Of course, you click save it. And then over here in your notebook on the right-hand side, you have to press the connect button. Okay, this will show up as connect. You have to click the connect button. Make sure that you have opened in playground. Okay, open in playground first. I'm getting messages. Guys, you have to open in playground first. And then you click on change runtime, click runtime over here, then change runtime type, then select GPU. If somebody is not able to change runtime type, or you're not able to select, you have to open it in playground. You have to open it in playground, guys. You guys need to open in the playground. There's an option for open in playground somewhere over here. It's quite big. It's right there on top. Okay. 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 I think most of people have got it. For those who haven't, the link that you open, you'll see Open in Playground over here. You click on Open in, instead of code and text, you'll see Open in Playground. You click on Open in Playground, it will open in Playground. And then you go to runtime, and then you go to change runtime type, and then you select GPU. Okay, we'll have to use GPU, guys, otherwise it will take a long time to train. So yeah, I think we'll just get started with the actual stuff. Okay, so in this webinar, we'll be learning to build an image classifier using PyTorch. And it's not about the data set, it's about how you actually approach the problem. And we'll be focusing on how we can how to actually build your custom deep learning model in PyTorch. And at the same time, I'll be showcasing some of the latest libraries in the PyTorch ecosystem, okay, which make using PyTorch very easy. So PyTorch historically has not been very newcomer friendly, and recently in the last 6 months, there have been a number of new libraries that have added uh, into the PyTorch ecosystem. And right now, using PyTorch is actually very simple. Okay. And by the way, this notebook will have these blanks where we'll be filling in. There's also a master notebook that you can actually access in this repository. Uh, it's called image classification underscore master. Okay, just in case you guys miss something, you can go and check it out over here. And yeah, so yeah, let's get started. So guys, the first thing you do in any machine learning or AI data science project is you get the data set on board. Okay, you get the data. In any real life problem involving AI or machine learning, getting the data on board is the hardest part. Getting the data, cleaning the data, pre-processing it, these are actually the most difficult parts. So machine learning models are usually not that difficult. They usually turn out to be the easiest parts. The most hardest part is getting the data. In our case, we are going to get a little lucky because PyTorch comes with a few set of data sets, and we'll be using one of those inbuilt data sets. This is called the MNIST data set. I'm pretty sure most of you have probably heard it if you have ever tried to do any machine learning or AI problem. This is usually considered the hello world of AI ML world. This MNIST dataset, everybody who learns starts off with this. And it basically contains 60,000 examples of handwritten images, which is the training set. And then there's a test set, which has 10,000 examples. So we'll be using both of these. Apparently, there's even a larger set available from NIST. We are, of course, not going to use it. PyTorch comes with a module called Torch Vision datasets. This particular module has a number of inbuilt datasets, and of course, MNIST stays there. We'll be importing MNIST from there, directly inside our Colab environment. So what do we do? First, we import some important libraries. We import Torch, of course, because this is the PyTorch library. You import Torch. You import Torch Vision. Torch Vision has the datasets module. Okay? Torch Vision, of course, relates to computer vision. It has all these image-based datasets. And from Torch Vision, we also import Torch Vision transforms. We'll be not actually using transforms, but just one bit of it, and I'll explain why we are going to use it. Then we'll be using a sampler called subset random sampler. So you import from torch.utils.data.sampler, import subset random sampler. What it does, we'll see it in a while. So guys, next we have to import some data science regulars. Oh, shit. Hello? Guys, can you hear me?
Yeah, we can hear you, Pranjal.
There was a power cut. Can you hear me, guys? Yes.
Yes.
Okay, perfect. So there was a power cut, and the power came back immediately. Okay, I've turned on my speakers. Unmute. Oh, everything seems to be. I have unmuted. Okay, okay, sorry for the disruption. Okay, so some regular data science libraries, we are going to import pandas, we're going to import numpy as np, and we're going to import pandas, although we are not going to use pandas, but it's just something, these two come together. Import pandas. So we execute both the cells. So guys, how do you execute cells in Colab? Is you do a shift enter. Okay, you do a shift enter, and your cell will get executed. If you're confused, you just click on this, and there's a play button. This play button basically executes the cell. You can also do a control enter to execute. Okay, both are the same things. So let's check out the dataset, MNIST dataset documentation. Okay, this is a screenshot from the documentation, PyTorch documentation. So you can see torchvision.datasets.mnist. It has these particular parameters. First is root. Root is the directory of the dataset, okay, where the dataset is going to be saved. And train is, this is important, please take a note of it. If train is true, it creates a dataset from training.pd, otherwise test.pd. That is, if you set it to true, it will download the training dataset, else it will download the test dataset. And download button, of course, if you set it to true, it downloads. And where it downloads in the root directory. This is important, guys. We'll be coding it right away. And then third is the transform. Okay, the function transforms taking a PIL image, basically image, and it returns a transform version. We'll be using transforms, but for a different reason. Target transform, it's a function transform that takes in the target and transforms it. We don't need it. So some of the work has been done for you. So you have the transform is equal to transforms that two tensor. I'll come to this, what it is. But right now we have to write, okay, we have to download the train data. So how do you do it? You do datasets dot mnist. Okay, we have imported datasets from here. So you do a datasets dot mnist, and in bracket you write root. This is the directory where you're going to download. So you just write data. You're going to download it right here in our Colab workspace. Root is equal to data. Train is equal to true. Okay, and we said download. Train is equal to true because this is a training data. Okay, this is not the testing data. So and of course you want to download it. So download is equal to true, and then transform. Okay, and if there is, if your line of code goes too long, you can always use this backslash and press enter, and Colab will automatically align it for you. So you don't, it's not good to write very long lengthy lines. You always break them in two parts. So transform is equal to transform. Okay. Similarly for datasets dot test data datasets dot mnist, similar stuff, and then you write root. You have to save it in the same directory. You do not save it in different directories, else PyTorch won't be able to read it. Train is equal to, train should be true or train should be false. What should be the answer, guys? Should we have train equal to true, or should we have it as false? Let's see if you guys can tell me. False, yes, correct. It has to be false because you're downloading the testing data set. Yes, this has to be false. And then you have to do download equal to true. Download equal to true. And of course, in the next line, I'll do transform. Okay, so some of you might be having questions. Why do we have a transform over here? And why have a transform at all? And what is the use of this transform? So the answer to the first question, why do we have a transform over here, is these images are of course in a different format. Okay, these are in an image format, and before putting this data through our PyTorch model, we have to convert it in a format that PyTorch understands. And PyTorch understands tensors. Okay, that is the only thing that PyTorch understands. So that's why we want to transforms to, basically transform the images into tensor. So this is the command for it. Transforms dot to tensor will basically transform it into a tensor, transform the image into a tensor. And why do we have transforms at all? So we have transforms because see, this is the problem itself. Our data itself is simple over here. Okay, this is basically a toy data set. It's called MNIST. But in real world, you have multicolored images. Okay, colored images, RGB channels, and you're detecting a lot of complex things. You're trying to classify complex day-to-day daily objects, and at that time you would want your model to train as robustly as possible on your data set to have a very robust training. You basically, what you do, you actually distort your images a little bit on, like you basically do random transforms. You randomly twist it, you randomly turn it, you flip it randomly, you add noise. So what happens is that the model trains on a much difficult data set than what is out there, and in turns, and this basically helps it to become a more robust classifier. So it performs better on the actual test data set and actual in real world outside. So that is why you have transforms. So anyway, we are not going to have some fancy transforms going on. We just convert images to tensor. Tensor, by the way, is a ground level data structure of any deep learning library, including PyTorch. So yes, we'll be using tensors, of course, throughout, and I'll explain a little more on what tensors are in a little while later. Okay, so we have downloaded our sets. So you just do a shift enter and it will download. Okay, transform. Okay, it should be transforms dot. Oh, I accidentally.
It's a typo. It's just a spelling typo in line 6.
Yeah.
Transform is equal to transform. So you have to change in line 6. There.
Okay. Thank you. Thanks, Helena.
Thank you to the chat because people saw it before.
Is it?
So okay. I'm not gonna take any credit.
Sorry guys, I'm not looking at the chat, but yeah, thanks for pointing it out. Yeah, so you download it. Okay, it gets downloaded. How do you check it? So on your left side, you have this sidebar over here. You have this folder option. You click on folder option, and what you'll see a data folder. Inside the data folder, you have MNIST. Inside MNIST, you have processes and all. So that means you have downloaded this data folder. Wasn't there before, so you just download it. Okay. Close it. We move forward. Now we do a test, train, validation, test, split. So obvious question, why we are splitting it? Because we have already downloaded training and testing data. We just start off with training the model, build the model and train it. But that's not how we do. What we do is we in almost every deep learning problem, you take your training data set and you split that training data set into 2 parts. One part becomes the training data set, which is your training data set. And the second part becomes your validation set. Okay. So the validation set is where you actually test your model. So you train it on the training set, and then on the validation set, you basically test it. And there are a number of hyperparameters of every deep learning model. So we fine tune our hyperparameters on the validation set. We do not do that on the testing set, because if we start fine tuning our model on the testing set, that means we are basically overfitting. So you might ask, what is overfitting? So overfitting is nothing but rote memorization of the data. So what would happen is that your model will get really great results on the test set, but as soon as you take it out and in the real world, it will start giving really bad results. So that's why we create a training, validation, and a test split. And the test and the training set gets divided into 2 parts: training and validation. And there's no set formula for rule of thumb for as in a formula for how much you want the training set to be, converted into actual training set, and how much you want to convert into validation set. But a usual rule of thumb is 80-20%. So 80% is training set and 20% is validation set. So your training set gets divided into two parts. One part, 80% of it becomes the actual training set, and 20% becomes validation, where you test it. So how do you actually create training and validation sets from the data that we have downloaded? We can use a simple 3-line algorithm. You create a list of indices of the training data, and then you randomly shuffle those indices and then slice the indices into 80 and 20 split. Okay, you can actually check out this nice answers posted somewhere. And why do you create a validation set at all? By the way, guys, throughout this notebook, there are a lot of these links, these kind of links I've posted. I mean, they are like sprinkled throughout the notebook. Make sure you read them after the webinar is over. For all those who are starting off with deep learning and AI, your work does not ends when the webinar ends, your work actually starts. Okay, so make sure you go through all of these. So, okay, we start off with creating a set, basically testing, training, and validation set. The first thing we do is create a list of indices of the training data. So we do a num train. Okay, num train is equal to length of train data. We want to see how long it is. Okay, and we can also print it. Print num train. Okay, can do. It's always good to print and see what is going on, guys. This is a good practice. So you're never in the dark about what just happened. Okay, we do indices. So we got the length of the indices. Now we create a list of these. Okay, so we do a list. We do a range, and then inside you do a num underscore train. Okay, and then we also print this. So we see print. Okay, we don't print this. We just do a length of this. We do a length indices. So ideally both should be the same. Let's see. Yeah. So num train is 60,000 and length of these indices is also 60,000. I don't want to print it, else it's going to be a 60,000 long list. So by the way, just in case you guys don't know what does range does, what is the purpose of range? So let me show you a really nice Python trick. If you do not know what, okay, Google is giving me warning that I'm not using the GPU. Sorry, Google, not yet. So it's so a nice trick in Python is, if you do not know about a particular function, okay, what it does. Let's say I don't know what range does. So there's something called as a doc string. Okay, you can do something like this. Let's see if it works. Yes, you can do a doc string instead of going to Google, opening a new tab, searching, coming across thousands of results. You simply do dot underscore underscore doc underscore underscore. These are double underscores, and you print it. So what does range do? It range, it's basically this is what it does. It starts and stops. It creates a range object. It returns an object that produces a sequence of integers. So that's what I did over here. I produced a sequence of integers and I converted it into a list. Okay, this is where I typecast. So I'll be using this print whatever function dot underscore underscore doc underscore underscore a lot of places. Okay, this is a very neat trick. It saves you a lot of time and also looks quite cool, I would say. So randomly shuffle. Now we got these indices. Okay, now we got these indices. We need to randomly shuffle them. So we use NumPy, and NumPy has a function called np.random, and random has another function called shuffle. So we basically shuffle them indices. Okay, and again, if you guys don't know what numpy.random does or something like that, you can always do print np.random underscore underscore dot. This is like a pro Python programmer technique, guys. That's it. You got a lot of, this is like coming from the documentation right away. This is what you actually look for when you do Google. Okay, when you Google for this, you just get it right away, and a lot of different things. Okay, we don't get into that. So okay, so we have split we have randomly shuffled our integers, and then we go into actually slicing them into 80-20 splits. So the validation size is going to be 20%. So I do a 0.2. Okay, so I make a split. So split is equal to integer. I'll basically typecast this into an integer just to be sure. np.floor makes sure that I do not my slice doesn't have an overflow. I do an np.floor just to make sure. I do a valid underscore size multiplied by the number of indices I have for training. So this is num train. Okay, this is the split, and then I do a train index, comma validation index, yeah, validation idx train valid. Okay, yeah. So then I do an indices. Then I split. So I basically split the indices based on this split that I just got. So this will be split colon. Okay, this is a slicing. We are slicing the indices, and then you do indices split. And a good thing over here would be to just print out the length of these. Okay, print len train underscore idx, and then you do a print len valid underscore idx. Let's see how much it is. So this looks like 48,000, 12,000, 60,000. Yeah, this is an 80-20 split. This verifies. Guys, use print commands profusely when you're coding, especially in deep learning. Okay, this makes sure that you do not have any errors. Just keep verifying whatever you're doing. So we prepared the data loaders. After data loaders, I'll take up questions. There are a lot of questions. Okay. So of course you have probably figured out that we are just being fiddling around with the indices. Okay, we are not the actual images. We downloaded the images over here, but we just split the indices. It doesn't make any sense. So now you know why we did that. Now it's time to prepare the data loader. So what is a data loader? Okay, so data loader is basically a mechanism to push your data into your PyTorch model. Okay, it's PyTorch has a module called data loader, and this is a very good analogy. Okay, so your data loader basically feeds batches of data to your deep learning model. That's what your data loader does. It has a lot of parameters, of course. I mean, it has a lot of complex stuff, but yeah, that's what it does on a higher level. And these are two data loader tutorials. I would suggest you guys go through both of these. Why? Because a normal genuine question would be that, hey, this data set was inside PyTorch. We just downloaded it, and we're going to load it into a data loader. But what if I have my own data set? What if I have my own custom data set? How do I use the data loader? So these are the two data loader tutorials you should totally check out. So what does data loader, what the documentation says about data loader class? Data loader combines a data set and a sampler, okay, and provides an iterable over the given data set. So basically you iterate over a given data set and push it into your PyTorch model. That's what you're going to do. And data loader supports, well, a lot of things. So you have input as data set, then you have to tell it what batch size. So batch size is, guys, we do not, when we are training a model, you do not just, push one image at a time. You push a number of different images. So you like push 10, 20, 30, 40, or even 100, or even thousands in some cases. 1,000 images in a single training pass. You get the results, and then you repeat the process. This usually enhances the speed of the training, and it is also, by the way, it's a kind of a hyperparameter. Batch size is a hyperparameter, although in our case, our data set is very simple, so we do not have to play around with it. Otherwise, you have to tune your batch size as well. You have to do a little bit of hidden trials and figure out the right batch size so that you get the highest amount of accuracy. Shuffle, if set to true, then you shuffle a data sampler. defines a strategy to draw samples from the data set, we'll define a sampler, because if you remember, right on the top, we imported a subset random sampler. So that makes sense. Okay, so we'll be using a sampler. Shuffle must be false. So if you provide a sampler, shuffle should be false. And batch sampler, number of workers, we are just putting it 0. You use it. I mean, you use it if you have a multi GPU rig, or you're training on different number of different GPUs. That's when you use it mostly. The rest of these are mostly not of much use to us, so I just skip them. So now we have to define the samplers for obtaining training and validation batches. And of course, remember, we use train IDX and valid IDX where the indices were shuffled above. So that's why we do not have to we just shuffle the indices. We did not went through with actually shuffling the images, because PyTorch will do the heavy lifting for us. So how do you do it? You do a train sampler. You write a train sampler is equal to subset random sampler. You do a train IDX. Okay, now Google Colab will help me write faster. Valid sampler is subset random sampler, and you do a valid IDX. Okay, you just pass on the indices. Subset random sampler will do everything for you. You prepared a data loaders, number of subprocesses to use for data 0. Do not modify this. This might crash your program right now. And number of batches, this is a hyperparameter. You can increase or decrease it. Right now, I'll be using 20. I found that you get superhuman accuracy with 20 batches. So, well, we'll just go with it. So training set first is done for you guys. Torch.utils, that's how you basically create your training set. Torch loader, okay? This is how you put your data in the data loader. Torch.utils.data.data loader. And in data loader, you get the data set, you pass on the data set. This is your training data, this is your data set. Then batch size, you have defined number of samplers, training sampler. Sampler is equal to train sampler. So it's going to sample from this training sampler. And then you have number of workers, you set it to 0 basically. So now we write code for validation loader. So what we write for validation loader, we can simply copy paste, but with one thing in mind, okay? You can copy paste this. Okay, but what you need to do is data set is going to be train data, batch size is batch size. Sampler is going to be valid sampler, okay? You're going to use the validation sampler. Sorry, Google, not yet. Google is again warning me. And then you do a num workers is equal to num workers, okay? That's that. Now we have to write the test loader. So the thing is that we do not have to use the sampler over here, because in the test set, you're not sampling anything. So you can again just copy paste, okay? Again, just copy paste. But data set is going to be test data, okay? And batch size we do not, we put batch size and number of workers, and we remove this, we do not need it. Okay, then you execute. So, okay, this executed fine, there was no errors. That means our data loaders are working. But of course, as I said, guys, you should always make sure that whatever you do, you're verifying it using print statement or some kind of visualization. So right now, we cannot use a print statement to visualize 60,000 images. So we have to do something clever. So we have to basically write a visualization code for it. And this is arguably the most important part of this particular webinar, and also when you are writing your own PyTorch models, okay? And I'll tell you, and you'll realize it, in a while. So first is we have to visualize a whole bunch of data from the data loaders. And the documentation said that, well, what the documentation says is data loader basically provides an iterable over a given data set. So in order to use the iterable, what you're going to do is you could do data iter is equal to iter is a Python function, okay? And then you do a train underscore loader. So I'm basically telling Python that, okay, this is an iterable. This will basically pass an iterable to my data iter variable from the train loader. Then I extract images and labels. So this data set will have two things, the images, of course, and the labels. Labels are the ground truth. Okay, labels tell you what actually the number is that has been written in the image. So I do this and I do a next data iter dot next. So in case you guys don't know what iter is, simply do print iter dot underscore underscore doc underscore underscore. Python will tell you what it is. Next, what we do is very important. We of course see the length of images and labels. This should be 20 because our batch size in 20. So this is basically passing us the whole batch of data. Okay, and this batch has to be 20. Okay, because we said batch size is 20. And I'll also print out the current labels just to see, and you print out the images. So before you print the image, you have to convert it into a numpy array. Okay, and this is how you convert it into a numpy array. You just do a dot numpy. This basically converts the image into a numpy array, and the library for visualization that we are going to use is going to be matplotlib, which is pretty much a de facto standard, and it understands numpy arrays. It does not understand tensors, so we have to convert it into a numpy. And the shape of our images tensor. Okay, shape of our images, not tensor. This is basically shape of our images batch. The shape of the batch is the single most important thing, and you'll know when we'll be creating the model. Okay, so you set the batch, and I think we are running a little slow. It's 840, and then of course, we want to know the batch size. There's a way to infer batch size. Of course, you set the batch size for 20, but from the images itself, you can infer the batch size using images.shape 0, and then you can also see the height and width of your images. So let me just do this, and it's better if you see it. So of course, this is the labels from correct labels. This is a tensor, by the way. Shape of our images batch is 20, 1, 28, 28. So this is technically a 4-dimensional tensor. Okay, this is a 4-dimensional tensor. The first dimension is the batch size. Second is the number of channels. This tells me it has 1 channel, which basically implies it's a grayscale image. And then the size of the image is 28 by 28. So the batch size is 20, and the image and image height and width is 28. Okay, and by the way, you can actually remove spurious dimensions from your images. So if you do an np.squeeze on your images, it will basically remove this spurious 1 dimension. Although in our case, it holds a meaning. It is the color channel, but NumPy will simply remove it, and it will make it 20 cross 20 cross 28. And at the same time, you can unsqueeze it, and you can add additional dimension. Okay, you can do a NumPy.expandDims and add dimensions on the 3rd axis. So 3rd axis would be 1, 2, 3. So over here it will add. So it will add over here. Okay. So the thing is that why I'm showing this to you, because when you're creating models in PyTorch, adding and removing dimensions should come very naturally to you. If you don't know how to do this, you will actually end up into a lot of errors by creating models. So we do a PyTorch. So we do a visualization. We import matplotlib, and this is a good image to understand what matplotlib models are. A figure contains the axis, which contains the axis inside where you have the plot. And this is a very, very good tutorial in matplotlib. Guys, please do check it out. So here I plot it. So I create a figure. This is the size. I think this is in centimeters or inches. I'm not sure, but this is the size. This works well. And then I iterate over the whole batch of 20 images. Okay, and I add a subplot. Okay, basically I add these x's. I add a subplot which has 2 rows and 10 columns. And for this particular indices, I'll basically populate the image. And I do a numpy.squeeze because I'm already specifying that this is going to be a gray channel image. So I just do a numpy.squeeze. When I do a numpy.squeeze, I basically get a 28 by 28 matrix. And I do a set title, which is the actual. I do a set title, and for set titles, I use the labels. This is the actual label. So you see 3, 8, 8. This is a 3, it looks like 8, wow. This is a 3, this is a 5, 0, 3. Okay, you basically print out everything. I do x ticks equal to blank, y ticks equal to blank. That's because I didn't want any ticks. So you see all these ticks over here, these marks, these are the ticks. I set them to 0. And a little neat NumPy trick. Okay, if you NumPy comes with a number of print options. If you define these print options, you actually get a kind of an ASCII image. So what you see over here is ASCII. Okay, this is ASCII version of the image. And you see these are the numbers. This is where the value is. Everything else is 0. By the way, this is a normalized image. So that's why you see the values only varying from 0 to 0.99. Okay, we move forward. Data loaders are working. And now time to build the model. Okay, so well, should I take the questions, Helena, or should I take questions in the end, because I don't want to run out of time?
I think maybe we have some questions, so it's up to you. If you want to do it at the end, we can do that. That's fine as well.
Yeah, I think we do it in the end. Guys,
Yep,
just keep
perfect.
typing your questions. I'll try to answer very quickly in the end, because in the end I don't want to run through the important parts. It's okay if I run through the questions. I mean, I can take my own time while answering your questions, but running through the actual part, it's not fun. So we start building PyTorch, and well, this is how somewhat how a PyTorch, a convolutional neural network kernel works. This is how it kind of scans. We'll see it. We'll see how it works. So we go through a very simple CNN architecture. This is a typical CNN architecture. By the way, check out this block, which is there as the tooltip. So you have an input image, okay, and you see these three squares because this is an RGB image. RGB image has 3 channels. So this is 3, and you have these kernels. Okay, these are called kernels or filters. In PyTorch, we call them kernels. So these CNN kernels actually scan these images from left to right. Okay, and they give you an output. So you get an output. Okay, this is like the convolution network's output, and then you add, then you have a pooling layer, and then you had more convolution, then you had a pooling, and it grows. Okay, this goes deep. Basically, that's why these are called as deep neural networks, because you have multiple deep layers of convolution, one after the other, max pool convolution, max pool convolution, and then in the end you flatten this. Okay, you flatten this into a layer of perceptrons, which is called a linear layer in PyTorch, or fully connected. Okay, this is called a fully connected layer. These are perceptrons. You flatten this box, okay, this cube, into, sorry Google, not yet, into a set of perceptrons, and then in the end you basically classify them, whether it is car, truck. In our case, we have 0, 1, 2, 3, 4. By the way, you guys need to notice something, that we start off thin. Okay, this block of convolution starts off thin, and by the very end it becomes very thick. So this is what we actually try to do. We basically increase the depth. Okay, this is called as the depth. We increase the depth of our convolutions. Okay, and we reduce the size of them. So what essentially we are doing is we are trying to capture the most important features from each of these different convolutional layers. Okay, and in the end we are kind of confident that the last layer has the most important features, and these are the important features which classify this image perfectly, which basically this is a car, image of a car. Okay, this is what we do. And an important thing to notice over here, this is a real life architecture of VGG16. VGG16 was a neural network, CNN based classifier from University of Oxford, which I think won the award in 2014. I think the ICLR, or there's a competition. Okay, it won that competition. Yes, Krishna, thank you for thank you for that. Okay, so in VGG16, what happens? You input this image, which is 224.224 cross 3. 3, this stands for the channels. And then you notice there is a max pooling layer. Okay, this yellow layers are the max pooling, and then you see you reduce the size of the dimension. This dimension gets reduced. And then again, the max pooling comes, dimension reduced. With the convolution, you can see the thickness is increasing. Eventually, this becomes really thin and really, very, it becomes very deep. So the initial few layers capture the most, capture the most important low-level aspects of any image. The initial few layers will capture mostly edges, and the last few layers capture the high-level high-level features like this is a light, this is a wheel, or this is a windshield, okay, something like that. So if you actually visualize these different convolution layers, you can actually see that this is looking at the edges, and this is probably looking at, the. By the way, this is the fully convolution connected layer. This is the last convolution layer. This is actually looking at some high-level features. So, so in the initial few convolutions, we tend to ensure that they have more or less the same size of the image dimensions, because we want maximum information to transform from the image to the first layer of convolution. And then, of course, we apply max pooling layers and we reduce the dimensionality. So we move forward. Well, this is very similar to the network we are going to use today, but not exactly the same. Okay. So you put in your images. It's a 28 by 28. We just saw the dimension of our images, and then we move forward. Okay, we put in a number of convolution layers. We're not going to use max pooling just to reduce the complexity of our network, and in the end we have a fully connected layer, and then we just do it. So how does CNN layer works? Okay, how does a CNN kernel work? So you have a CNN kernel. In this case, this is a 3 by 3 kernel. This yellow thing is a kernel, and it scans the image from left to right. Okay, and this kernel has some weights. Okay, in our case, these weights are 101, 0, 10, 101. These weights get multiplied by the actual pixel values, and then there is a element-wise summation. Okay, and that summation value is what you see over here. This is how convolution works. So in a colored image, we have three different channels. So one for R, G, and B. There's 3 channels, and this is like an example image. And this is how convolution will work for an RGB image. Okay, this is a convolution kernel, and it moves from left to right, and whatever are the numbers, it just keeps adding them. And in the end, just goes and gets added element wise. And by the way, check out this blog. There are a lot of different kinds of convolutions, so make sure you check out those convolutions. Okay, this is a very nice blog. So we move forward, and there are a number of parameters of our CNN. We look at those. Of course, there's stride. Okay, stride makes sure ensures defines how the convolution is moving, convolution kernel. Okay, if the stride is 1, it just moves 1 step at a time, both forward and on the right. Okay, it just moves 1 step at a time. Similarly, this is a stride 2. Okay, and padding is basically, sometimes you have to add padding. Why you add padding? Like in this case, if you look at the image that is being scanned, this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, this is 5 by 5 image. It is being scanned, and the output is also 5 by 5. Why do we do this? Sometimes in the initial layers, you want maximum transformation, maximum information to get into your neural network. Okay, so you add a padding so that there is no, the kernel can completely scan this. Otherwise, it will not be able to completely scan this. And max pooling. So what does max pooling do? Max pooling basically scans each sector of the output of the CNN and just reduces and only takes the highest value in this particular window. So in this particular window, this is a 2 by 2 max pooling here. It takes the maximum value over here, which is 20, and then it moves forward. In over here, the max value is 30, and over here it is 112, and this is 37. Of course, there are a number of different kinds of pooling layers. So check out this blog. This is a very nice tutorial on pooling layers. Okay. Pooling layers basically reduce the dimensionality. And then you have, of course, the nonlinear activation function, which is ReLU. ReLU is a nonlinear activation function, which is a very simple activation function. It is 0 if the values are negative. So if in case there are some negative values, okay, although it's not the case in our particular case. But if there are some negative values, it is 0. Otherwise, whatever is the value, it will pass on that value. And why we add activation function, the answer can be very complex. But just to understand right now, we add activation functions to add nonlinearity in our model. So we are basically trying to classify images in a highly nonlinear space. So it adds nonlinearity to the model. In the end, of course, you have the fully connected layer. You basically flatten this volume of tensors. You flatten it, and you get you basically, in the end, you classify it. If you have multiple classifications, you use a softmax. If you have a binary classification, you tend to use a sigmoid. And if you have a regression problem, you just use the logits. You just use these outputs directly. So questions before we move forward: what kind of features do the first few CNN layers capture? You guys can put the answers in the chat window. What kind of features do the last few CNN layers capture? What is the role of maxpool? And can we use stride to perform a role similar to maxpool? Okay, what this maxpool is doing, it is just converting this big CNN output into a smaller output, into a smaller one. Okay, it's basically reducing the size. You can also do that if you have a stride of 2. This is your input and this is your output. So you can do that, but do you think you should do it? Well, the answer is no. You do not do that, because maxpool captures the most important layers, most important features, while stride will simply just scan it. Okay, scan it into a smaller form. So you do dimensionality reduction using maxpool and not stride. However, in DC GANs, generated adversarial networks, you use stride to basically increase or reduce the size of your convolutional layers, but that's not what maxpooling does. So guys, we come to PyTorch, and of course, without getting into why PyTorch, PyTorch is the hardest library in the world right now, we understand why PyTorch is so flexible. Okay, so this is a simple neural network. This is a vertical image. Usually we print them out horizontally, so don't get confused. Every neural network trains like this. Okay, you have these nodes, and then you basically make a forward pass. Okay, these are the linear layers. This is simple neural network. This is a linear layer. This is a sigmoid. S stands for sigmoid. This is again linear layer, and in the end, you capture, you get the output and the loss. Now the thing is that you need to basically train this layer. Okay, so how do you train this? To train this, you basically figure out which weight contributes most to this loss, and accordingly you increase or reduce the weights. So for that, you make a backward pass, and you do a little bit of partial differential calculus coupled with chain rule. Sorry, Google, not yet. Coupled with chain rule, and you basically, in this particular case, we figure out, okay, this is how much loss is being contributed by W1. Now, for computer to understand, it has to see your program like this, like these nodes. Okay, and PyTorch basically makes these nodes in real time. These are called as computational graphs, and PyTorch makes these computational graphs in real time. So every time you're making a forward pass, you can basically, for the next time, you can actually change it. You can, L1 can connect directly to L2, and you can make these changes on the fly, and PyTorch basically converts these computational graphs on the fly, which makes it very Pythonic and very flexible. So this is a good example. You declare these weights, and as you're adding these operations, it is creating this computational graph, so that when you make a backward pass, it it basically figures out the gradients. These are the gradients. Okay, del L by del W1. These are the gradients. It basically calculates the gradients on the fly. So what are tensors? Tensors are basically hyperdimensional arrays. Like we just saw, we are right now dealing with a 4-dimensional array. Don't even try to visualize it. So we have an array of 20 cross 1 cross 28 cross 28. So tensors are nothing but arrays. Okay, so we just keep it simple. By the way, in physics, tensors can be something very, very complex, but in this case, these are just hyperdimensional arrays. This is how you define an array, and of course, arrays can reside on GPU as well as CPU. And this is what makes them super fast. If you have a array on a GPU, there's a lot of, you have to do a lot of computations, as we see, and it has to get very fast. So PyTorch can put them everything on the GPU, and you can always move GPU, move the array to move the tensors to your GPU or move them off the GPU. It's very simple. You can check this out. Of course, now we come to AutoGrad module. AutoGrad module is omnipresent in PyTorch, except that you don't actually see it. This is the module that actually calculates these gradients, these partial differential calculations. Okay, it does something called automatic differentiation, and you use a requires grad if you want to enable tracking on a computer on a tensor, or you do a detach if you don't. And if you want to use your model for inference, which we'll be using, you do a torch.node grad. Of course, there are a number of things. I'll just skip them because I'll explain them while I'm writing the code. And these are some of my favorite tutorials on PyTorch. Make sure you go through each one of them, guys, especially the first one. I really love the first one. So we start defining our model, okay? So to define our model, we have to use the convolutional layers in PyTorch, and we'll use the 2D convolution because, of course, we have a 2D image. And it takes in channels and outputs some channels, number of channels you want to take and a number of channels it outputs from convolution, size of the kernel, stride, and pattern. Okay, we know all of this. We also check out max pool. I'll just skip this. We're not going to use max pool. And we use dropout. So in dropout, why do we use dropout? We'll be using dropout, I'll tell you where. We'll be using dropout over here, okay, in the linear layers. So dropout basically randomly drops out with a particular probability these connections between these layers. We do this to make sure that we are not overfitting on a data set. We'll get to the overfitting very soon. And then, of course, in the end are the linear layers. Linear layers are the fully connected layers that we just saw. They take some input features and output some output features. Well, there's an important, interesting anomaly that you guys should check out is that convolutional layers take input channels and output channels, while the linear layers take features. So how do you actually combine these two? Okay, and this is where the biggest confusion comes up when we are using PyTorch. So these are channels. This is outputting channels in the code, and this is where you're taking input features. So how do we do it? So I found a really nice blog. I've taken some excerpts from it. So when you're torch, you need to know what PyTorch expects from a tensor dimension. If you have a one-dimensional tensor, PyTorch expects it to be a batch size. Of course, these are not hard and fast rules, but if you want to go against them, you have to do a lot of code. It will get very complex. But well, so PyTorch expects batch size. If you have a tensor of just one dimension, it expects it to be a batch size. If you have a two-dimensional tensor, it expects it to be a batch size, comma, number of features. And this is what you use for linear layers. Okay, remember this. We'll be coming to it. And then again, we can ignore this. If you have a four-dimensional tensor, which is batch size, comma, channels, comma, height, comma, width, this is what a convolution layer expects. This is what we have by the way today, 20 cross 1, cross 28, cross 28. And of course, if you are using 3D convolutions, you'll have one more dimension. So how do you convert a 2D tensor, sorry, a four-dimensional tensor into a two-dimensional tensor? You use dot view. So in dot view, what you do is, well, the first size has to be the batch size when you're using a linear layers. Okay, so you just tell it first size has to be the batch size, and then you do a -1. The -1 basically requests PyTorch to figure out everything by its own. Okay, so this is a really great article. Please check it out. Explains everything in detail. Before we move forward, guys, important questions before we start coding again. What is the shape of our images? What are the dimensions of our images? Answer in the chat window. What is the size of our batch? I need answers, guys. What is the size of our batch? How many channels are there in our images? People are answering a lot of different things.
Batch is 20. Yes, the size of our batch is 20. What is the shape of our images? Shape of our image is 28 by 28. And number of channels, how many channels are there? The number of channels are, well, 3. Wrong, guys. We have 1 channel. Yes, we have 1 channel, guys, because this is a grayscale image. MNIST dataset has a grayscale image. Anyway, so this was the most important part. Okay, we'll keep coming back to this. So if you actually see the shape of your images batch, it says 20 cross 1 cross 28 cross 28. So this one is your channel. This is your grayscale channel. Okay, this is a grayscale image. Okay, so we start coding again. By the way, this is a good visualization of how it looks. So this is how you'll be pushing your data into your convolutional neural network. This is going to be the batch size. These are the batch sizes. And the image depth in our case is just 1 because there are no 3 channels. This is a grayscale image. And then you have image height as well as image width. So we start coding. So we import some important libraries. NN module is the most important module in PyTorch. It contains the layers that you're going to define. And NN function is also similar to NN, but we'll see where we are going to use it. Some of the work I have done for you already. So, okay. So whenever you're defining your model in PyTorch, what you have to do is you have to create a class. I call my class MNIST model 1. Okay, I can call it anything, literally anything. Okay, so I call this MNIST model 1, and I subclass it from NN.module. Basically, I inherit from NN.module. And then you define 2 methods. One is def __ init, and another one is going to be def forward. So in init, you basically define your network, and in forward, you define basically what is going to, how your network, how your different layers are going to be connected. So we are going to do a little bit of math. The next line after init has to be super MNIST model 1. This is the name of this class, self.init. What we are basically doing is we are initializing the init method of this class. Okay, by super, you basically initialize this method. And a little bit of maths we have to do. Okay, why? So what shape dimensions the first layer is going to see? Okay, this is a question for everyone. What shape or dimensions the first layer is going to see? Okay, and do we need to have some padding for a kernel size of 3? The first layer is going to see 20 cross 1 cross 28 cross 28, and for the time being we can just ignore the batch size. This is what it's going to see. And if you want to have padding, yes and no, both answers are not wrong, but we need to know why. Okay, so input features are 1 cross 28 cross 28. Okay, this is what is going to be this is what the first layer is going to see. Okay, ignoring the batch size. What are going to be the output features? See, the output features, we need to understand what is the shape of a convolutional layer. Once you apply a convolutional filter, what is the output? Okay, what is the shape of this? So it is defined by W minus K plus 2P divided by S plus 1. W is the width, the height of the previous layer. In our case, it's 28 because this is what it's going to see. Okay, so width and height, remember width and height, guys. Remember from this image. And filter size, we are going to use 3 because it works well. If you keep padding is equal to 0 and stride is equal to 1, let's see what is the output shape. The output shape comes out to be 26. So basically it's going to be 1 cross 26 cross 26. Okay, but the problem is, if you remember, when we discussed CNN, that we want to have as much information from the first layer. So we want to make sure that we do not have 26 by 26, but we have 28 by 28. So what we do, if you do a padding of 1 and you calculate it, it will give you an output as this formula will basically give you 28. So that is where you need to do a little bit of calculation. And well, we start coding. So you do a self dot, you define a layer. Here we are just defining a layer, guys. Self.conv1 nn dot conv 2d. Okay, in channels are going to be how many? How many channels, guys? How many channels the first convolution layer is going to see? Can I see the answers? 1, yes. 1 is the answer. In channels, out channels is what you define, okay? Well, I want them to be 8. This is where you get a good response. And then you see a kernel size. Kernel size is equal to be 3. And then, of course, I want to add stride and padding. So you see this white line. This is Google Colab telling you, okay, you should not ideally go beyond this. So I do a backslash, and I've written kernel size. I do a stride is equal to 1, and padding equal to 1. Okay. So the output from this is going to be, output is going to be 1 cross 28 cross 28, and then we add another layer. We'll have 2 layers, okay, because 1 layer is not fun. The input is going to be from this layer to this layer, okay. When you're writing it among the layers, it is easy. So it's going to just take this output from this layer. It will have 8, and I say, let's say it outputs 16 channels, not too many, otherwise we'll start overfitting. And the output is going to be, I think it's going to be 28 by 28 only. Yep. But number of channels will now increase. Okay. So this is going to be 8. The number of channels is going to increase. So first, you'll push in 1 cross 28 cross 28. The outcomes 8 cross 28 cross 28, and from this layer outcome 16 cross 28 28. Now what we need to do, we need to find out what shape the first linear layer is going to see. So now since we have calculated, it's going to see 16 cross 28 cross 28, which is, well, this figure 12,544. So you can see this can balloon very quickly. These are just 2 convolution layers, and we have 12,544 features. That's a lot. So if I fill this self dot linear 1, well, if I do linear 1 is equal to nn dot linear in underscore features. In features, I have 1, 2, 5, 4, 4 features. Oops. And out features is something that I can define. Let's say I say 256. Okay. And from this, I do another, I define another layer. I can just copy paste now. And I define 3 layers. So this will be layer 2, this will be layer 3, and this will get input features as 256. This is coming from this layer to this layer, so it just passes on. And this will be 64, and this will be 64, and this will be 10. Why in the end I'm adding 10? Can somebody tell me why I added 10? This is going to be my last layer. I'm adding output features as 10. Can somebody answer me? Okay. Well, answer is written, by the way. Because we have 10 features. Okay, we are trying to classify 10 different images: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so last linear layer should have 10. So, well, I can just put it over here. This makes more sense. Okay, and dropout. We'll have some dropouts. So just make sure we do not overfit. Dropout p is equal to 0.25. Please equal to 0.25 tells dropout that to drop different connections in the fully connected layer with a probability of 25%. So now we define the forward pass. Okay, now this is where things are interesting. We'll add our so forward pass takes, of course, the self and the batch. Okay, this is the batch that will keep flowing through this. Okay, when you're training it. So I do an image batch is equal to first thing that I need to do is I need to add an activation. F dot value. This is where F comes into play. Okay, this is functional. torch.nn.functional. Okay, F dot value, and value has input equal to self dot convolutional layer 1, and I do an image batch. So I run my image batch through the first convolutional layer, and then I apply the activation. Okay, and we do something similar for, and once this batch has been applied, went through convolutional layer 1, we do again for convolutional layer 2. Okay, we do again for convolutional layer 2. We just change it to convolutional layer 2, and then you have this. Now we are going to pass. We have two convolutional layer guys, and now we pass it from the linear layer. So imagine we need to remember how what the linear layer expects. Linear layer expects a two-dimensional tensor. First dimension has to be the batch size, and second dimension has to be, and the rest of the dimensions, you just let the PyTorch figure out, the number over here. So what you do is I call this flat image batch is equal to image underscore batch dot view, and I need to put in the batch size. And how do you calculate the batch size from your batch, from your image batch? We go back to the most important part. Where was the most? Okay, I forgot where was the most important part. Yes, the most important part is this. This is how you figure out the batch size. You do images.shape bracket 0. So basically you basically go for this number. Okay. And what we do is we do an image underscore batch dot shape, do a 0, and then ask PyTorch to please figure everything else out for us. Okay, that's what we do. And then you basically do, then you just move it through then you just pass it from the linear layer. Flat image batch is equal to, and you do an activation, and then you do input is equal to self dot linear 1. We are passing it to linear 1 right now. Flat image batch, and time to add a dropout. I'm adding a dropout between linear layer 1 and linear layer 2. So this will be flat image batch is equal to self dot dropout, and you do a f dot value with input is equal to self dot linear 2. Okay, linear 2, and then of course this is a flat underscore image underscore batch. Okay, and yeah, we have passed it through the second layer, and then the final layer, flat underscore image batch is equal to f dot value. Okay, and input is equal to self dot linear layer 3. This is the third linear layer. Of course, flat input image. Okay, and we'll return just the logits for the time being because we'll do some fancy things later on. Flat image image batch. You run this. This won't throw an error, but okay. Now we install an interesting library, guys. We want to make sure that our model is working fine, and let's see if we can peep inside it. So there's a nice library called Torch Summary. We installed Torch Summary right now. You just run this, and you run this again. I think we are going to go past our timeline for this workshop. Okay, so now we actually have to make sure, now we actually see how our model looks from the inside. But before we do that, we have to tell PyTorch where to keep our model. Okay, where to keep our model on which device, whether you want to keep it on the CPU or the GPU. And over here we have the GPU enabled, so we'll keep it on the GPU. Okay, so this is a nice, what I'd say, a Python idiom. So it is called, that's how you write it, torch.device. And you do CUDA if torch.CUDA dot is available. Okay, else you put it on the CPU. Okay, and I'll just print it out. This is where the model is going to run. So now it's time to instantiate the model. So we instantiate the model by calling mnest or mnest class, mnest model 1. Okay, and we move it right away to the device which is available. In our case, this is going to be a GPU. We basically do a .to and whatever the device. And over here we do a summary. So how do you can get the summary of your device, of your model? So how do you get it is you do a summary. This summary imported from Torch Summary. Okay, so model is equal to mnest1 and input underscore size is equal to 1 cross 1 by 28. This is the images we are going to push in, guys. Okay, and batch size is going to be 20. So let's see. The model will run on CUDA. That's great. Okay, so this is a summary. Okay, so we have two convolutional layers. Then we have a linear layer. This is the third layer of the model. This is the second layer, and then in between we had a dropout. We added a dropout, and this is the final layer. Total parameters 3.2 million. So this is a very small, very basic model, guys. This already has 2.2 million parameters to train. This is crazy. This is why you need GPUs, and this is why deep learning models take so much time to train. And this is going to be a 15 megabyte model, and of course, so we did a lot of calculation to create this model, guys. By the way, there is a library called Torch Layers, which is phenomenal. Okay, you do a similar, you write models in it like this. Okay, no calculations. It automatically infers the dimensions. Okay, these dimensions that we were defining, it infers them automatically. It will automatically infer that you'll be inputting 12,544 features. This is basically automatic dimensional inference. Unfortunately, it won't run on Colab. Otherwise, we would have been doing this workshop using Torch Layers, webinar using Torch Layers. Anyway, we move forward. We write now. Our model is there. It's ready. Now we write a PyTorch model, PyTorch training loop. So training loops in PyTorch are fairly infamous because they get a little complex and repetitive, and there's a lot of complication. So say hello to Putin. Okay, this is an interesting library created by, I think, the University of Montreal guys. And by the way, Putin came in 2018, and Torch Layers came barely 2 weeks ago. So Putin is a very simple library. Okay, and we'll be using Putin to write our loops, training loops. So we install Putin. It's very simple to install. Okay, and we'll just install right away. And from Putin, you export model. This is the core data structure of this library. And from Torch, you import optimizers. So we'll need an optimizer to train our network. Okay, So that back propagation that we discussed, backward pass, there is an algorithm that that you need to apply to optimize, make sure you get the right amount of waste, best amount of weights for your model. So for that you need optimizer, and you import this. And here we write a simple training loop. These are the few learning hyperparameters. Learning weight, I worked it out already. 0.1 works well. Epochs equal to 3. And you just write it down. You just define your optimizer. So optimizer equal to optim.sgd. And of course, you insert the model. Okay, model parameters. In our case, this is going to be PyTorch model dot parameters, yes. And learning weight, we said learning weight is equal to learning weight. LR is equal to learning weight. Learning weight. Okay. And have a loss function. Of course, loss function will help the optimizer to figure out how much loss is there. So we use nn.cross entropy loss. Okay, this will work well for us in our case. And then of course you instantiate the protein model. You do a model, and then you do a model equal to PyTorch model. If you don't have to write it, network is PyTorch network or our model. We are just using it interchangeably. Okay, optimizer is equal to optimizer. Then loss function is equal to loss function. This is so simple. Okay, and then batch metrics, we will be looking at the accuracy. So batch metrics is equal to accuracy. Okay, we should not go beyond this line. Okay, so we define the model, and then what you do is you move this model. You also need to tell protein to move this model to the right device. Okay, otherwise it will throw error. Moves to device, and then you write model. This is a lot like Keras. If somebody knows Keras right now, they will be happy to see that you can do some similar stuff with PyTorch now. So model unfit underscore generator, you do a train. Okay, so this takes in the training data set. So you do a train loader. Okay, this is the training data set, and then this basically will train the model. Okay, and then you do a validation set. So you do a validation loader. These are the loaders we got from above. And number of epochs. Number of epochs is basically how many times we are going to go through the whole data set. In our case, we'll be doing it like 3 times. And yeah, and then you test on the test set. So what you do is no, test on the validation set, sorry. Okay, no, test on the test set, right. Testing loss, this is for the testing, test that starts. Test underscore accuracy is equal to model dot evaluate underscore generator, and this would be our test loader. The data set is going to be from the test loader. Okay, and we return nothing. We just run this, and it will start training. Wow, it just starts training. This is so easy. Okay, Putin makes everything so easy, writing the loops. Well, it will just train right away, I think. I think there's something, I think I've done something wrong. Have I done something wrong, guys? MS1, why we're training on 500? Oh, sorry. We train on the train loader, not the test loader. And that's why we had an error. So I have to redefine, redo this. Okay, and we do this. So I'll be retraining my same model. Yes. Now we are training on the training set. We were basically training on the testing set. And that's why there were just 500 images. This will take a while, so can we take a few questions? Although we are going to go past our webinar time, sorry guys, but yeah. Do we have any questions, Helena?
Would you like to take all the questions or?
We can quickly take a lot of questions, yes, although this was going to get finished now.
Yeah, so it's let me see if I can just so we have one general question is why anyone would prefer PyTorch over other libraries. If you can just give a quick answer.
Thanks, Frida. Okay, so why would anyone prefer PyTorch over other libraries? Well, because PyTorch is highly flexible and very Pythonic. You can actually create your custom models very easily. Okay, if you're creating custom models, of course, you have to go through a lot of maths, which is implied. Okay, it's implied that you know that maths. But if you want to create your custom models and do a lot of permutations, combinations with different layers, PyTorch gives you that flexibility, which is not there, which was not there in TensorFlow for the longest time. I think they have tried to make do with a lot of problems in TensorFlow 2.0, but still PyTorch is number one. That is why it is the choice of the researchers, because researchers, all these people are doing research on different models. They are actually, making a lot of different combinations and connecting one layer from different layer and having a new fancy architecture. So if you're trying to come up with something new, I think that's where PyTorch really shines. And also if you're just training it for your own purpose, PyTorch gives you a lot of flexibility. And with these libraries like Putin and Torch layers, you can just start off with PyTorch on the fly. Yes, next question.
Yes, and next question is from Sinta. What if we change the percentage of training and testing percentage? How much will it affect the result?
Sinta, if you do not have enough training examples in your for your model, then your model will not properly generalize on the testing set and when you deploy it in the real world. So you need to have enough training examples. There's no formula to it, of course. It's just something that you train and see if your model is working fine. But it's usually you have to give in deep learning, you have to provide lots and lots of data for your model to train. So yeah, training, of course, you have to have a lot of training data in the training set. Okay, yeah, next.
Yep, next question is, can we use flatten instead of squeeze?
Can we use flatten instead of squeeze? I think we can. I think it's something I have to check in the documentation. I think, yeah, we can use flatten instead of squeeze. No. Flatten and squeeze are doing the separate things. I think squeeze is doing something else, and flatten will probably do something what view is doing. I'll have to check. It is something I have to look at. I think if you look at the documentation, you'll know what flatten is doing. Okay.
Another question is, what should be the ideal ratio of training parameters and training samples in CNN?
The ideal ratio of training parameters
and training samples.
Training samples. Okay, so training samples, samples with the parameters, that's an interesting ratio they are asking for, but there's no set there's no set formula for this. I mean, I don't understand. I don't really understand like why do you want a training parameters ratio with training samples? I think that it would rather better be if we ask ratio of training set to test set or something like that. Although if you have too many parameters, okay, in your model, okay, and your training set is small, let's say 1,000 images or 500 images, you're bound to overfit. So make sure you do not overfit on your model. If you have way too many models, basically if you have way too many layers, if you have way too many linear and convolutional layers, and then you run your model on your training data set, you're going to overfit. There's no number. I mean, it's not something that I have quantified yet, but it's something that you need to understand that you do not need to have way too many parameters. That is not way too many layers. Okay, the 80-20 rule works fine. Yeah.
Another question is, what is logits?
Logits is the output from your linear layer. Okay, that's the final output from a linear layer. That's what you call logits. That is what we call logits. Okay.
So we have so many questions, and I don't think we can answer all of them, but I will pick a
Okay.
randomized one, just one random.
Okay.
So one is, could you please explain the purpose of flat image batch?
The purpose of flat image batch, that's a good question. See, why do we flatten it? We flatten it because of this. The convolutional layer takes input as in channels and outputs a number of channels, while the linear layer expects the number of features. Features are not equal to channels. And how PyTorch interprets an input to a convolutional neural network and a linear layer is that for convolutional network, you have batch size, channels, height, and width, okay, because this is working on an image. And then for the linear layer, you have a batch size, comma, features. So you basically flatten this output from your convolutional neural network into this two-dimensional tensor for your linear input, okay, because linear layer will expect this, and that is why you basically flatten it. That is the only reason, because up till here, where's the image? It's too far up. Yeah. So up till this point, what you have is basically some form of image, okay? No matter how small or how deep, this is some form of image. But from this point onwards, this linear layers do not take image. They take this data in a flattened format. That's why you flatten it. Okay, can we move forward?
Yeah, we can move forward. Absolutely.
Okay, so guys, before we move forward, we need to understand overfitting. Overfitting is basically what I've been talking about. Your model, if your model basically, fits too much on a testing set, and it's just basically memorizes the training data, and then it doesn't generalize well. So this is a good example of a good model which is generalizing well on the testing set. Okay, so high bias, this is a model with high bias which underfits. This is not a good set. If this is your data, this is not a good fit. And this is, of course, overfitting. This is the good one. This is the low bias, low variance. So we move fast. What we do is, well, of course, you want your validation. You don't want your model to overfit. If you train it for a lot of iterations, okay, we trained for 3 iterations just now. If we train it for like 20, 30, 40 iterations, your model will start overfitting. So you basically, the loss on the validation set will start increasing like this. So you probably want to stop somewhere over here, okay? And when you stop over here like this, it's called as early stopping. Well, so this is a good example. Initially, your model underfits on the data, and then it slowly starts overfitting. That you have to stop somewhere over here. This is a good matrix to understand, when your model is overfitting or not. I won't go into the detail right now. So to avoid overfitting, you can use a simpler model. This is an answer to the person who asked the ratio of training data to the number of parameters. So if your training data is small, then you should use a simpler model, because then you have less number of parameters, okay? And then you do not overfit. Use dropout layers. This is one way of doing it. This is called regularization. Use dropout, use more training data. If you have more training data, very good. Augmented data, okay, add noise. Use transforms, the transforms that we talked about initially. And of course, you can do early stopping. So we can write a better training loop. And to write a better training loop, what we do is we basically add some callbacks into the Poutine training loop. So Poutine library comes with something called as callbacks. Callbacks is basically a set of function that will run when the training loop is going on. So we import model checkpoint and early stopping. And callbacks in Poutine is basically a set of, it's just a list. This is just a list, and you basically fill in model checkpoint and you give the name of the model. Okay, on top you have the model name. You give the name, model name, plus this is basically I'm defining the name of the file name. Okay, last underscore epoch dot ckpt. This is just file name extension, and then you do. It requires a temporary file name. Temporary file name is equal to last underscore epoch. Okay, last underscore epoch. I just call it last epoch dot ckpt dot temp. Okay, and yeah, we have to add the early stopping as well. So over here we add early stopping. So we call early stopping. Is as simple as that. What we need to monitor, okay, you have to tell what you're monitoring. We are monitoring validation accuracy or accuracy and patience. So patience is for how long you want the protein training loop to wait till our condition for early stopping has met. So in our case, since this is a simple data set, I just say 0. Otherwise, it will wait for those number of epochs. Okay, and I said verbose equal to true because I want to know when early stopping is happening, and mode is equal to max. This basically tells that when the validation accuracy stops increasing for just one epoch, then you kick in early stopping. Okay, so you do this, and this is a nice tip. Okay, guys, make sure GPU is on because we'll be training for 10 epochs probably. So this is a nice tip to figure out what GPU Colab has given you. Colab has a number of different GPUs, by the way. So if you do a colon NVIDIA-SMI, it will tell you what, okay, I got a Tesla T4. Somebody will probably have a P4. Did somebody get P100 or something? Because P100 is the top end GPU that sometimes Colab will randomly give you. Did somebody got a P100? If somebody got a P100, please tell me in the chat. I'll be so jealous of you. Okay, so okay, let's fill in the CNN model. Okay, so we just copy paste from here. Okay, where was the model? Well, this. Okay, so you define the. I'm basically defining a new model because I don't want to retrain that same model. It will start to overfit. I call this MNIST2. And then I basically call this function, okay. Protein train, the name of my model is, we call this MNIST2, name is MNIST. You can call it anything. It's just, it will just use this to save the file, MNIST2. And I pass on PyTorch model, which is MNIST2. Okay, and I see if it runs. Yes, it is running. It will take a while, 3-4 minutes. Helena, we can take more questions. Wow, Anikesh, you got a P100. Congratulations. Asim got a P100. Wow, that's super. Okay.
You
so
ready?
Yeah.
So for CNN, how is Keras different to PyTorch for image classification?
How is Keras different from PyTorch?
Yes, for image classification.
Well, that's a very broad question. I think if you look at the API, you can actually tell. But what I've seen with Keras is I haven't used TensorFlow 2.0, by the way. But what I've seen with Keras is if you're just using the layers that it provides you, okay, and you're not doing something new, it works pretty well. Okay, but if you are in, let's say in the forward pass, I have to do something fancy with my layers. Okay, I have to do something fancy with my weights. Then it becomes a little complicated. That is where PyTorch makes things easy. So that's one way I think where Keras differs a lot from PyTorch.
Next
Yes.
question is, are there any data cleaning functions available in PyTorch?
Data cleaning functions. Well, PyTorch has some utils library, and it also has utils library for text-based, deep learning models. So yes, they do have some functions, but I think most of the things you probably have to do it on your own. If you're actually making a full-fledged real life deep learning model, you probably have to do a lot of heavy lifting for yourself. I mean, on your own.
The other question is, what made overfitting and underfitting happen with our data? Is it because wrong methods process used, or unclean, unprepared data, or what else?
So overfitting can happen to a number of reasons. If your data is not good, then you do not get overfitting. What you get is a bad performance on on the testing set and in real life and in real world. Overfitting usually happens if you have way too many layers for a simple data set. Like we have a simple data set, I just added 2 convolutional layers and 3 linear layers. If I added like 3, 4, or 5 convolutional layers and 2, 3 linear layers, then I would have started overfitting. So that's one. And of course, overfitting, like if you're not using regularization like dropout and max pool, then you can get overfitting. Yeah. Next question.
Which activation function is better for image classification, TON or ReLU?
ReLU. Hands down, ReLU works the best. It has been empirically shown that ReLU is the best function. I hope the question means the activation function in between the layers. For that, we use ReLU. Yeah, ReLU works the best. Of course, there are some new functions, activation functions from Google. I think it's called Niche or something, which has shown better results as well. But ReLU is the de facto. So you start off with ReLU and then you go into more exotic activation functions. So it's always advisable to start off with ReLU. Okay, so I go back to the problem, to the notebook, Helena. We'll come back to questions later. See, as you can see, you have this model. This model was just created by our Putin library. Okay, we did not do anything, nothing fancy. We just added these callbacks and we got the result over here. Okay, so of course I showed you guys a lot of plots. So is there a way to add plots? Yes, there is a way to add plots to this, to our training loop, and this is how you add plots. It's very simple. So you install this library called live loss plot, import plot losses Putin. This is a callback specifically for Putin. So you just instantiate it. You do a plot losses. Plot losses is equal to plot losses Putin, and you simply add it over here. Okay, you do a plot losses. It's as simple as that, guys. Just one line of code and you will have graphs. I train another network and I call fancy training model, fancy Putin train, sorry. This is the new model and I just call this and I basically call MNIST3, MNIST3, okay, yeah. Okay, oh, sorry, I have to execute this. Okay, function. Okay, wait. So you do routine model name, PyTorch. Did I do something wrong? I call MS3, yeah. Model name plus, okay, temporary file. Okay, this is working fine. And I add this plot losses. And callbacks. callbacks, model name, 3, PyTorch model. Okay, let me see. Let's see if there's something wrong. If I have, oh sorry, I think I didn't import this. Okay, so we are facing some problems. So let me just do it the way I do it. Model and PyTorch model, PyTorch underscore model equal to ls3, and it says the function has no attribute set underscore model, but I moved it to the device. Yes, I moved it to the device. Let me just try it one more time, and I'll just. I think I made some mistake. So best thing is if I just copy paste from this side. Okay, I copy paste and I put it over here. Okay, and I define plot losses is equal to plot routine losses. Yes, I add this. Okay, and I did all of this, and then move it to the device. Yes, ms3, and I move it. Now it's moved to device. Yes, and of course this is better. Okay, I need to change the name. Okay, and when I do this, wow, I have, this is supposed to work. Okay,
We have a suggestion for the plot losses is equal to plot losses protein and then the brackets.
Wait a second. Saying it's callbacks is equal to callbacks. Set model itself. It's supposed to work. Yeah, I think yes. I think that's the error. Okay, yeah, it works. Thanks, Helena. Okay, so we have some time. I will start plotting the graphs now. More questions? Yeah, live error handling. Yes.
Yes, always best with the live error handling. So that's how we learn together, right? So we have a question: how to decide value of non-workers?
If you are working on distribute, that's basically a fairly advanced parameter. If you're working on, if you have a number of different GPUs, or if you have a number of different CPUs, right? Then you actually specify num workers. Although some people have told me that if you have a multi-core CPU, you can specify num workers, but for some reason it throws error and it crashes on my system all the time. But yeah, that's why it is. I mean, you basically specify a different number of workers, and it will start loading your data set very fast. So if you go to that tutorial which I mentioned while I was talking about data loaders, the second tutorial actually discusses how you can load data in parallel from on different GPUs. So it's pretty interesting. You should check it out. Yeah.
Another question is, how is the thickness depth increasing while passing through convolutional layers?
Okay, Good question. I'll show you guys how or why it is happening. So when we wrote our model, so the input channels we took as 1, okay, in the convolutional layer, and the output channel was 8. So this is the thickness. So what you see, if you see the basic architecture, oops. So if you see the basic architecture, okay, this thickness is nothing but the number of channels that you have. So initially we had just 3 channels, then we added more channels using the convolution layers. Again, more convolution layers, more channels, pooling, more chairs, more convolution, more layers. So this thickness, this depth is nothing but the number of channels that you are adding through convolution. Okay, and through convolution, what you actually have is you are actually adding more layers. More, this 3 by 3 kernel. This is adding more layers. This over here I add 8 layers, and over here I add 16, and I can actually add more. Keep on. So this is why that volume is getting thicker and deeper because you're adding more channels. So that's why it's getting it's getting big. Next question.
Yes. Why is pre-training required in CNN?
Why is pre-training?
Yes, that is the question.
Well, I don't get the question. If the person who asked can please clarify, like, what do they mean by pre-training?
And then we have another. How do we decide when to use forward pass or back propagation in certain data?
Well, this is not something that you do. This is something that PyTorch will do it on its own. So this when you do make a forward or a backward pass is something that PyTorch does it when you call the training function like we did in this training loop, and it basically first moves the data in a forward pass, calculates the loss, and does a backward pass. So we don't have to worry about that. Okay, so Helena, I'll go back to the last part, which is the inference part. Okay, so we just added inference. Oh, sorry, we just added plots, and as you can see, as the valid error loss on the validation was going to go up, our early stopping kicked in, and we stopped with an accuracy of 98.6. And over here, you can also see there we have saved this model. Okay, this is the model that has been saved. And we write the inference. So inference is where everything will come back, whatever we have learned so far. Okay, this is the final part, guys. So for inference, what you do is you take your model and you do a forward pass, and then you see what results you're getting. So you basically take the model that you have already trained. Okay, so over here, what we do is first you instantiate your model, okay, MNIST model 1. This was the model that we defined, and you may move it to CPU because right now you don't need a GPU. For inference, usually you do not, okay? And then you do a model dot, this is a PyTorch command, load state dict, okay? Load state dict and torch dot load. Inside this, you give the command torch dot load path. So right now what we are doing, we need to understand what Putin saves for you. For what Putin actually saves, it saves the weights of the model in this file. Okay, so you're loading this file, and you're basically loading this file as a dictionary, and and basically sticking it on top of your model. Okay, this is the model that you define, and then you stick the trained weights in your model. Okay, this is how you load it. And of course, you can, just to test out, you can do a summary model, comma 1, comma 28, comma 28, and then device is equal to, you have to specify the device, okay, otherwise summary will throw an error. And what I can do is I just put everything as That's a comment. So yeah, so this is the model. This is the model that we have loaded. Okay, so this works fine. Okay, I can comment this out. I don't need this anymore. Now we have loaded the model. Now what we need to go, we need to get the test set. How do you get the test set? If you remember from the very top, the most important point in the whole webinar where I was pointing again and again, how do you get it? You do a data iter, okay, data iter is equal to iterate over a train loader. Okay, you have to iterate over this. And then you do in images, comma labels, you do a data iter dot next, of course, because there you get the data. And you of course get the ground truth. So label is equal to labels. So this will give us this is going to give us the training data set. I just pick the first label from the set. Every time it throws me a new new set of batches from the train loader. Okay, and this is the ground truth, and then the images will require a little bit of pre-processing. Okay, so image, you take image bracket 0. And what you do with this is, what I can show you guys is that print what is the dimension of this image. So image dot shape. So if I do this, sorry, it's images. It's 1,28,28. But the catch is that our model expects a 4-dimensional tensor. Okay, always remember, because what we were doing over here when we were setting the data loader, we were pushing our whole batches. And when we are pushing the whole batches, we had this one dimension, okay, which was the batch dimension, and this is the image. So we have to worry about this as well. You cannot just push in that value. Okay, so you cannot just push in 1,28,30. It will throw an error. So what you need to do is, comment this out, you need to add a new dimension, which is going to be the batch dimension. Okay, so torch dot, you can use unsqueeze. For adding extra dimensions in PyTorch, you use unsqueeze. For NumPy, it was a different function. So you do image, and you add a dimension over here. You add a new dimension over here, which is like 0. So you do a dim is equal to 0. And let's see if I do a print image dot shape. Let's see what I get. Okay, now this is fine. Now this is the batch dimension. So model expects a batch dimension. If you don't give it, it will basically throw an error. You'll have a matrix multiplication error. So we have done that, and now we make a forward pass. Make forward pass through the model. So you do but what we do is we need to turn off the autograd module. You turn off the autograd module because now you don't want to be accumulating those gradients. Okay, it's not needed, and it consumes a lot of memory as well. So you do a torch dot no grad. Okay, so you turn off the gradients, and then you make a forward pass. So you do output is equal to model dot forward. Forward is not renet, but it makes simple. We defined a forward routine, so we are making it. We are just passing it through it. Let's see if we get any error. Okay, we get an error. Oh sorry. I'm trying to hurry up. We are way past our webinar time. Sorry, guys. So now that we have done it, what we can do is we'll just show how the data is. So first thing I do is I go over. So what I do is what I'm getting from output as output from my model is the logits. Okay, I'm getting the model outputs logits. To convert logits into class probabilities, you use the softmax layer. Okay, so you do a torch.nn.f module. So you do that. That f has a softmax function. You input the model from the output, as in the output of the model, across the columns, and you convert it into a numpy and do a squeeze, and you basically print it out. And over here, I'm basically plotting the results. A little fancy way to plot it so that you guys appreciate what's going on. Okay, output is not defined. So, oh, sorry, output. So yes, so this is what the model is outputting right now, guys. So these are the class probabilities. They will vary from 0 to 1. And for the ground truth is 4. This is the image. And the class probability that the model is outputting is 4, which is correct, which is 100%. So over here, you can see 0, 1, 2, 3, 4. This is 1.0 and rest are like very small. They are there, but like very small probability. So if I run again and again, it will, keep throwing me different, different letters, different numbers, and the model will keep on predicting with near 100% probability. Sometimes it's not 100%. If you play with this long enough, you'll get a number which is not 100%. You just have to play around, with it. So congratulations, guys. We just finished. You just finished training your first deep learning model. I'm sure this was the first for a lot of people. And yeah, so thank you for staying with me throughout this webinar. We went way past our finishing time. I think we are running 35 minutes late. 35 minutes extra time. So thank you for staying over here. I'll be happy to connect with all of you guys over LinkedIn. And as a bonus, I'll be adding more content to this particular notebook. Okay, so I'll be adding transfer learning. I kind of figured that we'll be going over time with this. So I did not add these things. I'll be adding transfer learning. I'll also be adding how you visualize the graphs, the computation graphs of your model. This model that we have built, I'll add code to visualize that. And I'll also add code to how do you visualize your CNN layers. Okay, we added 2 layers in our model. Okay, so guys, we had 2 layers in our model, and how do you see what your model is seeing? So I'll add code for that, and there'll be a lot of explanation and comments, so don't worry. Okay. And please consider starting this repository. It is there on GitHub. You can click this link and check it out. And yeah, the notebook is inside. I think it's called PyTorch image classification in 2020. This is inside. You get the notebook. You also get the notebook which has the full code. Okay, which I prepared for you guys, and this particular repository also has my notes for deep learning from Udacity, and my peers at Udacity have already given a lot of love to this particular repository. So if you like the work, if you like the webinar, please start. So I think with this, I'll finish the webinar, and I'll start my video feed. So we had no issues, thankfully. It all went well.
All went well. Thank you so much, Pranjal. And amazing presentation as always. I told you, everyone, he is the Rockstar webinar instructor, and I was right. So you're giving a lot of thanks in the chat as well. And now it's actually time for Anna. Anna Unger is the lead from Facebook Developer Circle. So if you can stop sharing your screen and she can continue with hers, Pranjal.
Yeah.
Hi, Anna. How are you? Are you there?
Hi, yes, I'm here. Thank you, everyone. I have a problem. Yeah, share my screen. Okay, so now I see you can all see my screen. And since we're running out of time, I want to start collecting feedback from you. So either you could go to menti.com and use the code 940181, or you could use a QR scanner to scan the QR code, as you see. Oh, I got 1 heart from someone. Thank you so much. So I will go to the first question. have you used PyTorch before this webinar? So why we want your feedback is because we want to continue doing these webinars, and we want to improve. So we want to listen to you, what you want to see and hear in the future. So I can
people are replying in the chat.
There, yeah, I see. Yes. Okay, so please reply in menti.com. Yeah, thank you. And the code is 940181. Perfect. Yeah, so I can tell you the background, how I got in contact with Facebook Developer Circles. It was when I studied at Udacity. I think it was together with Helena, and Pranjal was also present, right?
Yeah, we were there.
Yeah, everyone,
Yes.
yeah, and many in the audience too. So as a student shared the link how to join the developer circles, and I tried to find a local circle, but there wasn't one. So I got the option to apply for starting my own circle, which I did together with 2 other leads. Yeah, great. People are still answering. Thank you so much. So one of our goals as a developer circle is to help people to connect. That's only one of our goals. Diversity is another important goal. And that is why I ask you all the time, like, where do you live? How old are you? And what is your gender? And I use this information in order to create diversity in our community. So I'm sorry, but I will go to the next slide. So my question is, has this PyTorch workshop increased your interest? Like, do you feel more interested in PyTorch after having been participating in this? Wow. Yeah, and then your knowledge. Do you feel you know more about PyTorch and deep learning after this webinar? And self-governance, do you feel that you have more ability on your own after this webinar to perform deep learning and using PyTorch? Thank you so much for answering, guys. Amazing to see that this seems have been quite helpful for people, Pranjal.
Thank you, guys. Thank you.
So because of lack of time, I have to move on to the next slide, which is about rating this event. So the first one is content. Do you like this content? And that is like the topic and how we did it, like the resources, and then accessibility. Was it easy to join this webinar? Did you get enough information prior to the event? Was it messy? Did we forget to send you a link? And so on. And the last one is entertaining. Did you find this webinar entertaining? Like, did you have a good time? Do you feel like doing it again? So again, really
Thank you, guys.
good feedback. Yes, so that was my last question. Thank you so much for coming, and we will try to organize something in a very near future, and we will ask you again a bit more about what kind of content. So watch out for an email about this. Thank you so much. Back to you, Helena.
Thank you so much, Pranjal, for this presentation today. You are amazing as always, and the rock star of this, you know it. And I'll say this in hi everyone, here I am. Thank you so much. Thank you, Anna, for organizing this through Facebook Developer Circles together with me from People in Data. And this was a great collaboration. I want to thank everyone who joined in today. Thank you so much. It's amazing to see everyone joining in and being so active and hanging out here in the chat as well. So I hope to see you soon again. Please stay safe, everyone, and take care of yourselves. And I'll see you soon, I hope. Have a lovely, lovely Sunday, everyone. Thank you so much. I'm going to wave now. Bye, everyone.
Bye. See you.
Bye.